Have you ever really stopped to think about what happens when you hit play on a movie? I mean, what's the actual physical journey your data takes just to get out of your own neighborhood? Well, today, that's exactly what we're going to break down. We're exploring the very first mile of the internet. I mean, seriously, how does it work? A movie file is sitting on a server somewhere, maybe hundreds, even thousands of miles away, and somehow it just magically appears on your screen. It's not magic, of course. It's an incredible system of physical stuff: cables, boxes, and light. So how does it really happen? The whole journey starts right at your front door, or maybe even the wall jack in your living room. The very first step for any bit of data, whether it's coming or going, is a trip across what we call the access network. This is the on-ramp, the physical path that gets you from your couch onto the global information superhighway. Now, to really understand this on-ramp, we got to get a few key terms straight. This is basically the vocabulary we use to describe that place where your personal digital world slams right into the huge global internet. First up, end systems. It sounds a little technical, but it's just the stuff we use every single day. Your computer, your phone, your smart TV, those are all end systems. But so are the giant servers that host websites like Netflix or Google. They're called end systems because they are the ultimate starting line or finish line for any piece of data. And all of these end systems, well, they sit at what we call the network edge. Now, this isn't a physical place you can go visit. It's more of a concept. It's the boundary line, the frontier where our private devices meet the massive public network that is the internet. Which brings us right back to the star of our show today, the access network. This is the physical stuff, the actual wires and gear that connects your device to the very first router it's going to talk to. You'll hear people call it the first mile or the last mile, and that's exactly what we're going to unpack. Okay, so for most of us connecting from home, there are really three main roads that make up this access network. We're going to look at each one: the old classic DSL, the workhorse cable, and the speed demon fiber. Our first road is the classic, the OG, digital subscriber line, or DSL. The genius of DSL was that it was a clever hack. It used the infrastructure that was already wired into pretty much every single home, the good old-fashioned copper telephone line. So let's just trace the path here for a second. It all starts at your computer, which is plugged into a DSL modem. That little box takes your digital data and turns it into a signal that can ride on your phone line, all the way to the telephone company's local building, their central office. And in there, there's a big piece of equipment called a DSLM. It's a mouthful, a digital subscriber line access multiplexer, that gathers up all the signals from your neighborhood and shoots them out to the internet. The best way to think of DSL is like having your own private country lane. That copper wire from your house to the phone company is all yours. You don't share it with your neighbors, which is nice. The catch? It's a pretty narrow lane. DSL is asymmetric, which means you can download stuff way faster than you can upload it. Back in the day, that was fine for browsing, but today, it can be a real bottleneck. All right, road number 2. This is the one that really brought high-speed internet to the masses: cable. This approach piggybacked on the infrastructure that was built to deliver cable TV, and those cables had way more bandwidth than the old phone lines. So the setup here is usually something called hybrid fiber coax, or HFC. Let's follow the data again. The cable company runs a super high-capacity fiber optic line out to a box in your neighborhood. From that box, a single, thick coaxial cable snakes through the neighborhood, connecting all the houses on your block. Everyone shares that same line. Then, back at the cable company's office, a device called a CMTS, a cable modem termination system, manages everything, kind of like the DSLM we saw before. So the most important thing to get about cable is that it's a shared highway. Sure, it's a big, multi-lane highway, way faster than that little DSL country road, but you're sharing it with dozens of your neighbors. So during rush hour, like at 8 p.m. when everyone is streaming a show, that fast highway can get totally jammed up, and your speeds can take a nosedive. And that brings us to the newest and, let's be honest, the best road on the block: fiber to the home, or FTTH. This isn't about reusing old wires. This is a purpose-built network for data, running impossibly thin strands of pure glass right into your house. So how does this lightspeed magic work? A common design is called a passive optical network, or PON. At the central office, a box called an OLT, or optical line terminator, turns electrical data into pulses of light. This light zips down a single fiber to your neighborhood, where it hits a simple, unpowered splitter. That splitter just copies the light and sends it down individual fibers to each house, where a little box called an ONT, or optical network terminator, turns the light back into data your router can understand. It's incredibly elegant. Fiber really is the glass superhighway. We're talking mind-bendingly fast speeds that are symmetric, which means your upload is just as blazing fast as your download. It's like having your own personal 10-lane superhighway with no speed limit and zero traffic running directly into your home. It's the future. Okay, so that's how the internet gets to our house. But what about inside? How do all our devices, our laptops, our phones, our game consoles, actually connect to that incoming pipe? Well, inside your home or office, it really boils down to two main technologies. For that rock-solid, super-fast wired connection, we use Ethernet. And for the freedom to roam around, we use Wi-Fi, where our devices connect wirelessly to an access point, which is, you guessed it, just plugged right back into that same wired Ethernet network. Now let's zoom in even further. We've been talking about these roads and highways, but what are they actually made of? What are these physical pipes that are carrying all our ones and zeros? Physical media really falls into two big categories. You've got unguided media, which is wireless stuff like Wi-Fi or satellite, where the signal just travels through the air. But the access networks we've been focusing on, DSL, cable, and fiber, all use guided media, where that signal is physically contained and guided along a solid cable. So let's look at our three data pipes. Twisted pair copper, that's what DSL and Ethernet use. Think of it like a basic garden hose. It works, but it can only handle so much. Then you've got coaxial cable for table internet. This is more like a wider fire hose. It's got a thick copper core and lots of shielding, so it can carry way more data. And then you have fiber optic cable. This is a massive industrial superhose. It uses light traveling through glass, and it can move an absolutely staggering amount of data. All right, let's pull this all together. It's time for the final showdown, a head-to-head comparison of the three main ways we get onto the internet from home. This chart lays it all out perfectly. You've got DSL using old copper phone lines for your own dedicated but slow private lane. You've got cable using a mix of fiber and coax for a faster but congested shared highway. And then you've got FTTH, fiber to the home, using pure glass to give you an unbelievably fast glass superhighway. So there you have it. The access network is just the on-ramp. It's the critical first mile of a much, much longer trip. Your data has now successfully merged onto the internet superhighway. But what happens next? How does your data navigate the millions of intersections in the vast, complex network core to actually find its destination? Well, that's a story for our next explainer.